Hello, fellow problem solvers. So today we're going to be doing our final part of this Introduction to Function series. And I was thinking for this, I could either give you a lot of different techniques, ways to solve functions, yada yada. But I realized it could maybe just be too much unnecessarily. And solving functions is, I think, one of the most fun parts of competitive mathematics, because you're literally playing with values. And you're trying to see, like, what can you get from functional equations when you say something, like you put these things into it and then you force it, come on, give me a value. And I think it's more fun, and also you will learn much better if you try to attempt to solve problems as opposed to just tell me all the possible tricks, right? You can solve problems and then figure out, oh, this thing exists, oh, this thing exists. For the beginning, I think I will leave you with just this other thing, which is that what a fixed point of a function is. It is a function from a to a. It is any x that's in a such that f of x is x. Why are these things important? Well, sometimes you're trying to prove f of x is equal to x. And really what you're trying to prove is that everything in a is a fixed point. So you could maybe be looking at subsets which are fixed points, and then you'll be able to expand them. And it's sometimes easier to think in terms of a fixed point like that and play around with that when you just know this terminology. Like, what is a fixed point? And if this is a fixed point and this is a fixed point, what else is a fixed point? That's one thing. And the other thing is sometimes a function maybe doesn't have a lot of fixed. Maybe you can only have one or two or a finite number of fixed points. And then if you have f of something is that thing, you may be able to know what that something is. Maybe f of 1 is equal to 1 is the only fixed, maybe 1 is the only fixed point. And then if you get f of something is equal to that thing, and there can be a lot of f's in that, you can maybe get something new. Right? If you only prove that f of 1 is the only fixed point. But that's this. Now, these three problems have three different ways, three different techniques, three different views of functions that I'll teach you. I invite you, every single one of them, try for a minimum of 10 minutes, ideally 30, not more than an hour, not more than an hour and a half, not more than 45 minutes. If you'd like to go along with us, we're going to start with the first problem. Give it a go for the next 10 minutes. Put your first ideas out on paper, and now let's begin. So, what do we do here? We have to find all functions from R to R. Okay, so because they're from R to R, we won't be able to do a lot of induction here. Such that, whoa, what's this? X squared plus y? Okay, that's doable. Then f of x to the 27th plus 2y? What? What is this? What is this? This doesn't look nice. And the way we do this one is we say, wait a second, we have two f's here, one f here. Can we get rid of an f? And how can you get rid of f's? Well, if we equalize two things, if we equalize the things inside the two f's, we can get rid of one. So we can get rid of both of them. So here we can either equalize this and this, or this and this. Let's see what happens if we were to equalize this and this. What would we need? Here I invite you to pause for 10 minutes and try to push the problem further. Because what we would get is we need that y plus x squared would need to be x to the fourth. In other words, we'd need to set y to x to the fourth minus x squared. And if we set this y, the function would imply that f of x to the 27th plus 2x to the power of 4 minus x squared minus 2x squared is 0 for all x. Because mind you, we've just set y, x can be anything. This goes back to what I've said before, you want to set the values in one after another. So this holds true for every x. What does that tell us? Well, if you've done anything with polynomials, you'll know that. What kind of polynomial is this? It's an odd degree polynomial, which means what? It means that it covers all the real values between negative infinity and positive infinity. So for any m that's a real number, we'll have an x such that this whole thing evaluates to m. Why? When there's many ways to think about this. One is that every polynomial of an odd degree has a real root. And from there it follows if we do this minus any m, it's a polynomial of an odd degree. It has one real root. Ergo, we can find something that minus m is 0, or something that evaluates this to m. But another way to think about it is polynomials are continuous functions. When m is negative, what is this? When m is going towards negative infinity, what does this look like then? And the answer is, this is incredibly negative. This is just like goes towards negative infinity. And then when m gets positive, what does this look like? And the answer is, well, this goes incredibly positive. So it needs to cover, like this is y is equal to this polynomial in the xy plane. So it covers all the values of y from negative infinity to positive infinity. So this just means f of t is 0 for every single t, and we're done. Now that's one way of going about this. And before recording this, I didn't know this was going to be a solution, but it's a pretty cool solution, if you ask me. The other thing is, if we wanted to equalize, what's it called, this and this, then we would need to have, again, y plus x squared would mean to be 2y plus x to the 27th. And then y is x squared minus x to the 27th. And then these two would cancel out, and we'd be left with f of x to the power of 4 is 0. Which means that, what does this mean actually? Pause for 2 minutes. It means that every positive real number is equal to 0. Actually, and 0 is also, f of that is equal to 0. So now we have the positives. How do we get the negatives? Well, this will always be positive. So let me set y to 0. And I have f of what? X squared is f of x to the 27th plus f of x to the power of 4. These two are positives, so f of x to the 27th is equal to 0 for every x. And now I can get all the negatives. What I just set x to be the 27th root of, say, the negative 27th root of z squared. Then this thing right here to the 27th becomes f of negative z squared for real z is 0. We have the negatives are 0. And this finishes up. Now we need to check actually that f of x is 0 works for every single x, and it's 0 is equal to 0 plus 0. It works. So with that, we're done with the first problem. And the idea is you have some f's on both sides, try to equalize them. Now, I invite you to pause for the next 15 minutes and try to figure out, first of all, what is this condition? For all functions, prove there exists a real number, from the reals to the reals, such that this isn't true? Wait, what? It's not asking us to find a function, but prove that no matter the function, there exists an x such that this isn't true? Pause for 10 minutes and try to push it from further, and also figure out what this is about. And here's the next step. So, it says that prove there exists an x no matter the function such that this is true. Such that something is not equal to something else. Well, the converse would be what? Assume the contrary. There exists a function such that f of x is always equal to this. And now we're trying to show that this doesn't have a solution in functions from R to R. Right? We've changed what we're looking at. Just by that. So now here I invite you to pause. If you didn't figure this out, pause for another 10 minutes and then we'll go to the next step. And here's the next step. So there are many ways to go about this. But I want to show you you can plug in specific values and figure out what to do. But I want to show you this thing about fixed points. So here, this side, if we look at this as a function in g of x, which we know what it is, how many fixed points does it have? it has how many? It has two fixed points, right? How many times is x squared minus 2 is equal to x? Well, this is true for, what's it called? This is an x squared minus x minus 2 is 0. This is true for, this is x plus 1 times x minus 2 is equal to 0. So for 2 points. I'll use the terminology, I'll call these points A and B. And now I have, G has 2 points. G of x has 2 fixed points. Now how many fixed points does the function g of, say, g of x have? It has, well, this thing is going to be, so this is equal to x if and only if this inside is equal to one of the other 2 fixed points. Or actually, let me just say, like, instead of that, this is going to be g of some x squared minus x minus 2 is equal to x. And how many fixed points does this have? Well, we know g of x for x equals a and b are already 2 fixed points. So here we'll have a polynomial of degree 4. This will be x squared minus 2. Minus 2 is equal to x. X squared minus 2 squared is equal to x. We already know that a equals 1, a equals negative 1, x equals negative 1, and x equals 2 are going to be fixed points. So we'll be able to factor that with this. And when we do, we'll have this is x. So this is going to be x minus 2, x plus 1. And then what we have, we'll have x to the power of 4. And when we factor, so this is x squared because we have x to the power of 4. Or in other words, when I actually factor this, we have, now why do I apply it like this? Because there's a way that we can look at this function now in 2 different ways. We have the points, call these points A, B, C, and D. And we know that g of A is equal to A, g of B is equal to B. And for points G and C, G and D, we'll have g of C is going to equal D, and g of D is equal to C. We can plug these in, or we can do a case-by-case analysis. What does this g go into? So we have g of x has these fixed points. And now when we try to look at this in 2 different ways, we can look at f of this is equal to f of g of x. But also, we can look at this as this function being g, f of something is g. So this is g of f of x on the other hand. So if g of f of x is equal to f of g of x. And now what happens with our fixed points? Well, if we evaluate f at a, f of a is going to equal to what? F of a is going to equal f of g of a, because g of a is already equal to a. But this thing is equal to g of f of a. And what does that make f of a? Well, that makes f of a fixed point of g, right? Because g of something is equal to that thing. So now f of a is either going to be one of the fixed points one of the g's fixed points, which is either going to be a or b. And similarly, f of b is also going to satisfy that as well. Now, I invite you to pause for another 10 minutes and see if you can push the problem further. And here's the next step in these fixed point analysis. And that's, so now we similarly look at f of c. What are these fixed points of g going to be? And this is showing 2 tricks. One is applying f of f and looking at it in 2 different ways. And the other one is fixed points. So f of c, we know that this is equal to f of g of c. But also we know this is equal to f of g of d. And now this is equal to g of f of d. Now, is this what we wanted? No, it's not quite what we want because we want a fixed point here. And however, we'll also have the similar thing for, we'll have f of d is equal to g of f of c. Now, what happens when I apply g on both sides? I'll get g of f of d. Well, this thing right here is going to be equal to what? Well, by g of f of d is going to equal f of c. And on the other hand, this is equal to g of f of c. So now f of c is a fixed point of g of x, which means f of c needs to be one of a, b, c, or d. And similarly, f of d needs to be one of these things. And now with that, I invite you to pause for another 5 minutes and try to push the problem further. And here's the next step. And the idea is, well, now, what is, say, f of c? If f of c was equal to a, what would we have? Well, if we, if we g both sides, we'll have g of f of c is going to equal to g of a. Now, g of f of c is going to equal, by this, is going to equal f of g of c. And g of a is going to equal a. And on the other hand, we're going to have this f of g of c is going to be what? F of g of c, we have c is a fixed, well, g of c is equal to d, so we're going to have this is going to be f of d. So if f of c is a, then f of d is a as well. And now, does this give us anything? Does this lead us to any contradiction? Well, the answer is, we're not there yet with a contradiction. This hasn't led us anywhere. So now what do we need to do? Well, we have f of d is also equal to a. We've applied a g. Let's apply an f first. On both sides, what do we have then? We have f of c, which is going to equal to f of a. Actually, this is equal to f of a on one hand. And on the other hand, this is also equal to g of c. And the reason this is equal to g of c is because that's what f is. F of x is g of x. So with this in mind, we have g of c is f of a, and g of c we know to be equal to d. And now we have d is equal to f of a, but f of a is either a or b. So this leads to a contradiction. So this means f of c cannot be a, f of c cannot be b in the same way. F of d can't be a, f of d can't be b. F of c cannot be c as well. Why not? Well, if f of c was equal to c, we would have a contradiction because, actually, pause for 2 minutes and you tell me, what would we have if f of c was equal to c? Where's the contradiction? The answer is, if f of c is equal to c, then we f both sides, and we get this is equal to g of c, which is equal to d on one hand, but on the other hand, we have f of c is equal to c. So we have d is equal to c, which is a contradiction. So f of c and f of d cannot be a or b, so they have to be, so we have f of c and f of d need to be in c and d. And now with that, pause for 5 minutes, push the problem further. Here's the next step. And so what do we have? We have this. Let's just keep in mind what it is we have. And now we have these things need to hold true. So now what happens? Well, when we set f of c is d on one hand, on the other hand, we can say f both sides, and then f of d is equal to c. On the other hand, f of c is equal to g of c, which we know is equal to d. And then we get c is equal to d, which is a contradiction because these are two separate zeros as we found. And this shows that actually f does not exist that satisfies this relationship. So we could have gone and looked at what these things actually are, the zeros of this function, of this x squared minus 2. But instead of getting into the nitty gritty, because C and like A and B aren't that bad, but C and D have a square root in them. Like when I calculated them, they had a square root in them. So instead of looking at those values, and you need to F stuff here to be able to deal with this in two different ways, you look at fixed points. And that is why I was also a bit hesitant on using this technique, but this is an example which uses it, and hopefully in other problems you'll be able to see it in a better way. And now let's finish up with our final problem. And this one take at most 45 minutes. Just try it out for 10. And here's the first step. So we have x plus f of x is f of x. We're looking when is f of x equal to 0. So what can we do here? Well, the answer is, when is this, what kind of a function is this? Here's where you look for injections. If f of a is equal to f of b, then f of a is equal to f of b. But then so is a plus f of a is equal to b plus f of b by the functional equation. And because f of a is f of b, that implies a is equal to b. So the function is an injection. And so there can be at most really, actually I'm not going to say anything just yet, but the function we know now is an injection. And now what would happen if f of x and f of y were equal? We're not sure yet. Like we would have x plus f of x is y plus f of y. We don't know things about x and y, so we're good. And we're looking to solve every time this is a 0. So every time x is equal to negative f of x. What would you do here? What is your next step? Pause for a minute now. And here's the big idea. Well, because I have an injection now, if I put f of x is 0, I'll get f of 0 is f of 0, which implies that f of 0 is equal to 0. And now, if f of x was equal to 0, which is equal to f of 0, this would imply that f of x is equal to 0. But then this is also equal to f of 0. And so by injection, this would imply that x is equal to 0. And that is why the only solution to f of x is 0 is x equals 0. Mind you, we did not solve the function. We don't need to do that. We just found every point such that f of x is equal to 0. And this solves the final problem. And it shows that sometimes, you can look for injections and they can help you finish a problem. So in this case, it was necessary. And this shows like how injections can just like kill the f's. Just like that. You just cancel an f. You get this is 0. I put an f here. Bam, bam. This is 0 again. Okay, and I put another f. This is also f of 0. Then bam, bam, x is 0. They can be really, really useful in this way. This finishes up our problem, and as always, thanks for problem solving.